So Bayes' rule converges to the true joint distributions of the parameters and the data, right? Posterior on all of your observations, which is a really strong guarantee, right? And you can actually prove that. But the assumption in the proof is that your prior has to put positive weight on that distribution. So if you assume a joint Gaussian distribution over your data, and your data is even a tiny bit different from Gaussian, that theoretical guarantee means nothing. Okay? So Bayes' rule makes strong assumptions, but if the assumptions are satisfied, it gives you a lot. Maximum likelihood. The typical result for maximum likelihood that people say is that it's asymptotically, it's consistent and minimum variance. That means in the limit of lots of data, you're going to converge to the true parameters, and you're going to have the minimum variance estimate of those parameters that's possible out of all asymptotically unbiased estimates. Again, there's a big if. Your model has to actually contain the actual distribution of your data. Like, for some set of parameters, you have to be able to model your data exactly. Otherwise, that convergence guarantee is off, and you go to only much weaker theoretical guarantees, right? I don't know about you, but I'm unwilling to assume that is actually exactly Gaussian, and so that guarantee is much weaker than it initially sounds. All right, so that brings us to empirical risk minimization. The sorts of guarantees that people prove for empirical risk minimization, and in fact we'll prove some of them today, are that if there's some predictor that actually performs well in your class, right? You don't have to be able to match the probability distribution, you just have to be able to predict. Then empirical risk minimization will be able to converge to a predictor that does almost as well, right? So that's by far the weakest assumption, right? You have to believe somewhere in your class there's a predictor that has some chance of succeeding. Otherwise, there's no point in this whole machine learning exercise. And once you assume that, you're able with empirical risk minimization to prove these guarantees. Now, on the flip side, right, the constants in these guarantees, or the asymptotic rates, might be weaker. Right? And the most typical situation is that the big O notation is the same, but the constants are worse in the proof. But you can have any situation, right? It can't be better than the optimal rate if you know the distribution, but it could be a little bit worse. So again, it's a trade-off. You assume some stuff, and if the stuff that you assume is true, good things happen. If the stuff that you assume is false, who knows what happens? All right? All right, so that's enough of the big picture for a while. Does that make sense to everybody? Questions about? OK, good. So enough big picture. Let's take a look at the perceptron. So we're in classification again. For example, character recognition, right? So you could have all of these different handwritten digits, and you could try and split them into two classes. So I'm going to call this class, let's say, 1, 1. -1, -1, -1, -1, -1, 1, and 1. OK? So I've labeled the classes +1 and -1 instead of 0 and 1. Hopefully that doesn't cause any confusion, but it'll be convenient for notation today. So given this labeling of those examples, anybody have a guess what the concept is? That's right, the closed loop somewhere in the character. So obviously, human learning is much faster than machine learning. I would expect the perceptron to need a few more than these 10 examples to be able to get that. Cool. So character recognition is one. We gave you the example of spam filtering in the previous lectures. About 1 billion different classification problems you could imagine. So the typical way to do this is going to be then to represent each one of your inputs with a set of features. So in the spam classification problem, you remember the features were things like the bag of words, the count of the number of times avocado appears in your email. For handwritten digit classification, you could have the individual grayscale pixel values of the images. That would be a reasonable feature. You could make, for example, SIFT or GIST or HOG descriptors of your images. Right? If you don't happen to know what those are, then search for them on Google. But the point is there's a ton of different features. Let's assume for now that I'm just going to take the matrix that's the grayscale values and string it out as a big, long vector and have those be my features. All right. And now, given this mapping of features to class labels, +1 or -1, what we have to do is we have to learn a classifier. The type of classifier we've been learning so far in naive Bayes and also in logistic regression, which is going to be coming up soon, is a linear classifier, right? So what we want to do is have the sum over all features. Let's say this, we have features j, we have example xi, feature j, right? And then we multiply that by some adjustable weight, wj, right? And we test whether that is greater than or equal to some threshold, which we'll call b, right? So this is a linear classifier. It's also called a linear discriminant function, right? And the reason it's called a discriminant is because it's discriminating between +1 and -1 classes, right? So you'll hear terminology sometime. And so our goal is going to be to adjust the weights. And the perceptron is maybe the oldest algorithm on the books for adjusting those weights. It's so old, in fact, that the first time it was implemented, the weights were stored in variable resistors. Those are like dimmer switches for lights, right? The features, they came from a 400 pixel CCD camera, right? So I don't know what, like 0.0004 megapixel CCD camera, right? And the weights were adjusted by actually having motors that turned the dimmer switches, right? So this is pretty old school. It was in 1958. It's called the Mark I perceptron. And so let's take a look at, by the way, on the homework, you're not going to be using dimmer switches. So let's take a look at how we might be going to learn this. All right. So like I said, we have a linear discriminant, which I wrote on the previous slide, actually, right? So this is the linear discriminant function. And we're going to assume, to start off with, that our data are linearly separable, right? We'll get away from that assumption eventually, but it's going to be easier to analyze what happens in the separable case. That never happens in practice, or almost never happens in practice, so don't go about assuming that on your class projects. But for now, we're going to assume that. And let's just simplify our notation a little bit. So the first simplification is going to be homogeneous coordinates, right? So we had, actually, the first simplification I'm going to do back on this slide. So I'm going to write this as a dot product between example I and a featured vector w, and that's greater than or equal to b, right? So what I've done is I've collected all of the features together into a vector, and I've replaced that sum with a dot product, right? And so up here, right, we have xi dot w is greater than or equal to b, right? And we have xi is an example that's a d-dimensional vector, right? And w, that's our adjustable weights, and that's also a d-dimensional vector, and the threshold b is just a single number, right? Okay, so just to simplify notation, what if the last component of every xi were 1, right? So in MATLAB notation, right, I comma end equals 1, right? So what if we assumed that? By the way, is it reasonable to assume that? Well, yeah, sure. Because if it wasn't true, we could just replace xi by a vector which was xi and then a 1 at the end, right? And set d to d plus 1, right? So it's reasonable to assume that. And suppose that's true, then we actually don't need this b, right? Why is that? Because if you have xi, so xi1 dot w and minus b, right? If that's greater than or equal to 0, that's the same as saying that xi dot w minus b is greater than or equal to 0, which is the same as saying that, right? So, so we can get rid of b. And so we just have, and I'm going to forget about the d+1 trick, and so I'm just going to assume that we have our examples that are in RD and our weight vector that's in RD, and our discriminant rule that we want is xi dot w is greater than or equal to 0. Okay? The other thing I'm going to do, right, and this we want to be true for if yi is equal to 1, and if yi is not equal to 1, if yi is equal to -1, we'd actually prefer to have xi dot w is less than or equal to 0. Oh, and I actually want, so I actually want specifically greater than 0, right? We don't want it on the boundary, and we want it specifically less than 0, right? Same thing here. I'll put specifically greater than b, right? And the option is xi dot w is specifically less than b. And so let's count it as an error if we ever get xi dot w equal to b. But with real valued features, how often is that ever going to happen, right? So we'll just pretend it's never equal to b, and we'll call it an error if round-off error keeps us actually exactly equal to b. All right? So we actually want to discriminate, right? We want to have a difference between, we'd be very unhappy if everything were equal to b, because then we wouldn't be able to tell the positives from negatives. All right, so then the next thing we're going to do, let's multiply both sides of this equation by yi, right? So multiplying both sides of the equation by 1, anybody want to tell me what the equation turns into? Yeah, I figured you'd all get that. If you multiply them both by -1, right? So this is the same as saying yi times xi is, dot w is greater than or equal to 0. And this one is the same as saying yi xi dot w. And now because we multiplied by a negative number, we flip the sign, and 0 times yi is 0. Right? And so that's the same in both cases. So now I'm going to be able to talk about all examples at once. If I just say that my discriminant is yi xi dot w is greater than 0 or not. Right? So this is now my simplified notation for the discriminant. And just to make things even simpler, I'm going to call this ui. Right? And so I'm going to say ui dot w is greater than 0 or not, depending on whether I get an error or not. Okay? So everybody understand the simplified notation now? I see some nods. That's good. Right, so in my training data, I've got xi and yi. In my test data, I'm not going to be able to do that second transformation. I'm just going to do a discriminant that looks like this, xi dot w is greater than b, and I'll check. And I'll say yi is whatever sign makes it correct. Okay. All right. So that's the notation. All right, so now the notation, right, this is just copied from the previous slide. We want ui.w to be bigger than 0 for all I, right? This is saying I don't make an error on the ith training example, which is a good constraint to have. And so the first algorithm that we're going to consider for finding a w that satisfies these constraints is linear programming, right? So those of you who have seen linear programs before, right, the idea is that you give them a bunch of linear constraints and they find a vector that satisfies them for you. So are we done? Can we just hand these constraints off to Cplex or some other linear programming software and go out and grab a cup of coffee? How many people think we're done? How many people think we're not done? All right. Again, everybody's going by the fact that I'm lecturing. Does anybody want to have a guess for why we're not done? What would happen if we did this? Anybody? These are strict inequalities. These are strict inequalities. That's right. So you'll get a type error if your linear programming software is smart enough, or if the linear programming software is not smart enough, it will just pretend they're strict inequality, non-strict inequalities instead of strict ones. What would happen if we just replaced all of the greater than by greater than or equal to? What would the software give us? 0, that's right. 0 is a very good solution to this equation if you have greater than or equal to, right? Set everything to 0, probably don't even have time to get our cup of coffee, right? But not very helpful. So what are we going to do? I'm going to define something. I'm going to define a number gamma, which is equal to the minimum over all examples I of ui dot w, right? And by assumption, that's strictly greater than 0 for, let's say, the optimal w, right? So this gamma, we don't know how big it is, but if it were, if we did happen to know it, we could then write ui dot w is greater than or equal to now gamma, right? And now we can give these to our linear programming solver, and it can't give us the trivial solution of 0, so it might actually take a little while. We go out, get our coffee, come back, and it'll give us a w that actually correctly classifies every single one of our examples. Now, great, but then we need to know what gamma is, right? Suppose we just set, cross out gamma and set it to 1, right? I'm going to say all of my gammas are 1. Seems like a crazy thing to do, right? Now, well then, fine. We knew that, so let's actually write these as two separate equations. Ui dot w is greater than or equal to 1 now, right? So we know that w star will satisfy this equation, right? So, and if we find w star, we're happy, right? Now let's think about w star over gamma, right? So if we divide both sides of this equation by gamma, right, we get w over gamma and gamma over gamma, right? So we get 1. And see, we know that w star over gamma is going to satisfy this equation, right? Do we care whether we get w star or w star over gamma? No, right? I mean, it's a line. It's got the same normal, right? We can multiply the normal vector by any amount we want, and it'll be the same line, right? So we actually used the flexibility that we have that we don't care about what multiple of w star we get. And now it's just OK to solve this, right? And we don't need to know what gamma is. We'll be able to find out gamma after the end of the optimization, but we just give that to Cplex, and we're done. All right? Kind of a clever trick. Remember it. You might see it again later in some other algorithm. Okay. So linear programming, that's a pretty decent algorithm. For small data sets, it's actually probably going to be the best algorithm. For huge data sets, billions of examples, right, every spam email that's ever been sent, most linear programming solvers are going to fall over if you try and give them something that's that large. So we need a more efficient algorithm. So what is that going to be? It's going to be the so-called perceptron algorithm, which was designed to solve perceptrons, hence the name. So what does the perceptron algorithm look like? So we're going to make a slight change. So far, we've been assuming that somebody gives us a training data set, and that data set has a bunch of examples of the form xi, yi, and that's all the examples we're ever going to get, right? And we have to take that big batch of examples and just learn, excuse me, learn from them. So the perceptron algorithm is for the online learning setting. What does that mean? That means that data are streaming in all of the time, right? There's a never-ending pipeline of data coming into our office. We can always look at the head of the pipeline, and there'll be another training example on it. And what we do is we get the xi from that training example, we make a prediction, and then we find out what the yi is going to be, right? And so we find out whether we were right or wrong. Then we get the next xi, we make another prediction, and we get the corresponding yi. So OK, online learning seems like a reasonable model. What if somebody actually does dump a batch of training data on us, right? Well, we can turn it into the online model by just going through our data set multiple times, right? We'll pick examples from our data set, and when we run out, we'll keep picking more, right? And we'll repeat examples, but we'll still get an infinite stream of examples. So this online model, it's not a restriction. It's just a slightly different way of thinking of the same problem. If you have a training set, you can turn it into the online model. And if you just have the online stream, you can still use the online model, right? Now in practice, you're going to get different performance depending on how you sample from your training. So I figured I'd mention that in practice, one of the best ways to do it is you take your training data set, you put it in a random order, like you select a random permutation, and you go through it in that random order. When you're done, you pick a new random order, repermute your data set, and go through it again, right? So you'll go through your data set. You'll see every example once before you see any example twice. But within each group of seeing every example, you'll do it in a random order. All right? So just in case you have to implement it, it's important to do it that way. Yes, no chance that we'll ever have to implement a perceptron. Right. So that's the way to do it. OK, so the perceptron algorithm, we're going to assume that we have this stream of training example. And we're going to do the following. We start by saying that W is equal to 0, right? We observe the next training point, which is xi, right? And so we predict, right? So this is now for I equals 1, 2, ... right? We'll predict the sign of xi dot w, right? If we're right, good. That's everything we have to do. Don't mess with success, right? If we're wrong, we will set w to w plus yi times xi, right? Why is this a reasonable thing to do? Suppose, right, we want xi dot w to be big, right? We want it to be positive, so we want it to be bigger than it was. So xi dot w plus, let's say it was a positive example, we want it to be big. If it's a negative example, we want it to be small. So for a positive example, what we'll do is we'll take w and we'll turn it into w plus xi, right? And so that's equal to xi dot w plus xi dot xi, right? This quantity is greater than or equal to 0, right? So this is greater than or equal to xi dot w, right? And so for a positive example, we've increased this dot product, and we're more likely to classify that same example positive in the future, as well as other similar examples, right? And you can go through this again for a negative example, and we reduce the dot product, make it more negative, and make it more likely to correctly classify that example again in the future. All right? And then that's done, right? This is the entire perceptron algorithm, right? So that's great. It's really, really simple to implement. It's a really simple algorithm. And we're going to actually be able to prove that it works moderately well. So that's kind of cool. Everybody understand the perceptron algorithm? Think you could implement it if we were to ask you to do so? Yeah? OK, cool. So convergence, yeah?
How fast does the perceptron?
Yeah, that's a that's a good question. So I guess the first question, actually, before how fast, is does it converge? Right? And in the linearly separable case, the answer is yes. It will converge, and it'll actually converge quite quickly. And I'll prove that in a few slides from now. In the non-separable case, sadly, perceptron does not converge. So we actually don't care whether the weights W converge themselves, right? We care about the direction, right? So the only thing that matters about the weights is their direction, right? But that also does not converge. And what winds up happening is that typically, if you're non-separable, it's going to wind up, you'll make an error, and that will move your direction of your weight vector, and then you'll make another error, and it'll move it around. And so the weights will, if they start off in some terrible place, they'll go to an approximately reasonable place, but then they'll just keep bouncing around potentially in that place forever. So that's not good, right? We want a vector that actually converges and preferably converges to something reasonable. So what do we do? The fix is going to be, we're going to define W bar to be 1 over n, sum from I equals 1 to n of Wi, right? So the weights after we'll call it W bar sub n, I guess, right? So the weights after n iterations, right? After every iteration, we have a weight vector. Some iterations, we won't change the weight vector, so it'll be the same weight vector for a few of them. Some iterations will change it. We average all of the weight vectors we've seen so far, weighted by how many times we've seen each one. We get that average, and we'll call that W bar. Okay? And W bar can converge even when W itself does not. And so that's what we're going to wind up analyzing in the non-separable case. And we'll show basically that the weight vector W bar has good training performance, which then guarantees through other stuff that we'll prove later in the semester that, that it'll have good generalization performance, good test set performance as well. All right? Yeah.
So W is the random vector, correct?
W is the weight vector, so it's the one that starts. So if we go back to this here, right? W is initialized to 0, and every mistake we update it with the yi times xi, right? So that's the weight vector of the perceptron, and we're using it in this linear discriminant decision rule to classify examples. Okay. Okay, and so it's not, I'm not going to say converges because it doesn't have to converge, but it will behave nicely for some future definition of nicely. All right, so I just wanted to mention that. All right, before we go and talk about what the perceptron is going to do in theory, let's think a little bit more about how to visualize what's going on and what's going to go on in practice, right? So what I've got here, this is a plot of some examples. I happen to put the examples on the unit circle, but there's no real reason for that other than that it looks pretty. I've labeled positive examples over here, negative examples over here, and this is my weight vector W, right? And so rather, this is my decision surface, right? And this here is my weight vector W, right? And if I bring that arrow over here, right, it's going to wind up looking like this, and it's going to be the normal to that decision surface, right? So if people don't happen to know that, for here, right, this defines a half space. This linear constraint defines a half space. The boundary of the half space is a line, and the vector W is always going to be pointing orthogonal to the boundary of that half space. Right. Here it is. Okay. So every example leads to a constraint on W, right? So let's take this example right here, right? So the weight vectors that classify that example correctly are going to be the ones that are on, that make less than a 90-degree angle with it, right? So if I draw that example here, right, it's going to, here's the example, right? And so the weight vectors that classify that example correctly are going to be the ones that have a positive dot product with the example. So that's going to be a half space in the set of possible weights, right? So I've done something kind of tricky here, right? I represent the weights by a decision boundary when I'm looking at examples, right? And I represent them as a vector over here in weight space because, in fact, here, right, there's two features, so we have two weights, and so the weight vector is a two-dimensional vector, right? So we can think of the two-dimensional vector either as a point itself or as a half space, right, a constraint in the example space, right? So now if I look at this guy here, right, this is also going to be a constraint on the weight vector, but because this is a negative example, right, I want I want the weight vector to make more than a 90-degree angle with it so that it'll have a negative dot product, right? So if I put it, right, graph it here on this, right, this is going to be the example that I've marked with a square, right? And so it's actually going to give essentially the same constraint, right? Maybe, slightly different constraint, but almost the same constraint. And then again, it'll be orthogonal. The example vector will be normal to that constraint, right? And the weight vector will have to be on the side away from the example as opposed to the side towards the example, right? And so if I take, let's say this one, right, that's going to be a vector pointing this way, right? And it's going to make a constraint on the weight vector that says that it has to be on that side, right? And so with these three examples, right, the valid weight vectors, the ones that classify all of them correctly, is anything in that cone. And if I were to put all of the examples, plot them all, there'd be a very narrow cone of weight vectors that classify all of them correctly, right? So is everybody okay with that visualization? Yeah. Cool. So this over here is called example space, and this over here is called weight space, right? Yeah.
So for the decision boundary in example space, you would have for just those one points, you have an infinite amount of lines that could correctly classify that?
Right. Yeah, you can wiggle this line, right, back and forth across some amount of some arc, right, and you'll still correctly classify these examples.
Okay, and so you're taking the kind of intersection of all of those and you get a...
Yeah, and that's right. You take an intersection of all of the constraints. Each example puts a constraint on the weight vector. And if you take the intersection of all of those constraints, you'll get a cone. And if you have only a few examples constraining it, it'll be a wide cone. And here, where we have a bunch of examples constraining it, it'll be a very narrow cone, right? And in high dimensions, it'll wind up being a cone in high dimensions, right? I could, maybe draw 3. I'll start to have trouble drawing higher than that. Basically, every example is going to wind up putting a constraint on the weight vector. And because we're assuming that everything is linearly separable, we can make it a hard constraint on the weight vector and take only weight vectors that correctly classify every example. Yeah?
You said only in the misclassification, or only during misclassification do you change your weight vector?
Right. So here I'm showing, right, over here, this is a weight vector, presumably after we've trained for a while. And this weight vector happens to classify everything correctly. This green one, although you might not be able to see it, is actually on that side, right? And so we're not going to update the weight vector anymore because we're not going to make any more mistakes. So I showed this after the perceptron algorithm has converged.
It seems like, well, so that then it's order dependent, right?
That's right. The outcome that you get from the perceptron algorithm is dependent on the order in which you present your examples.
Why don't they just do it? Maybe I'm just stupid, but maybe why don't they just do it for both cases, the specification and the classification?
You could, in fact, have an algorithm that updated your weight vector both on correct examples and on incorrect examples. That would be a different algorithm, and that might work too, right? Depending on how you did the update for the correct examples.
Is it usually worse?
Let's see. I guess we haven't specified what that algorithm is completely because we haven't specified what the update would be. I know perceptron's a pretty decent algorithm. I don't know for that one.
Geoff, I think the actual question, correct green points, so you get a reasonable estimate, and then you train all the red points, so you further.
Right, you could do that.
It's kind of just why not make it so it's not order dependent?
Oh, right. Well, so the linear programming algorithm is not order dependent, right? And it's more expensive, right? Its only failure is that it's more expensive, right? So the perceptron was originally designed to be a very fast, very simple algorithm to process the points just by skimming through them. It happens to be order dependent. That could be a flaw, but it doesn't matter very much. So people didn't bother to try and fix that. Other questions about perceptrons or about this visualization, example space and weight space?
So isn't this visualization basically drawing out the constraints of the linear program?
Yes. Yeah, absolutely. The question is, aren't we just drawing out the constraints of the linear program? And the answer is yes. But I wanted you to see what it looked like on a piece of, well, virtual paper, rather than just say, we write out a linear program. This is what that linear program means, right? You get this sort of narrow wedge of weight vectors that are consistent with all the examples that you've seen so far. All right? Yeah.
Is it possible that the weight vector has a different dimension?
Well, right. So in our decision rule, right, it's ui.w or xi.w, right? And so in order to take the dot product, the weight vector has to be the same dimension as our examples. Now, you can change the dimension of your example, and then that changes the dimension of your weight vector. For example, you could add, if you had features x, y, and z for your example, you could add x squared or x times y or the cosine of z as a feature. And that would change the dimension of your examples, and the weight vector would come along too. It would have the same dimension as your modified examples. Okay. All right. More questions? All right. This same sort of visualization that we did before, we can do, so this case, right, it was, the half space was through the origin. Now, if we have two-dimensional examples and then add a 1 at the end of every example, we'll have a three-dimensional example and a three-dimensional weight vector. But you can still visualize it in 2 dimensions if you want to. And what happens is that you get a half space that just doesn't pass through the origin. Right? So that's fine. So what are we going to do in that case? Well, so the weight vector here, right? This weight vector, if we transfer it over here, it's going to look like this, right? And it's still going to be normal to the decision boundary, right? It'll be orthogonal to the decision boundary. But the decision boundary, like you'll have to shift it a little bit, right, in order to actually touch the decision boundary. You can work out, the other thing, I guess, in this case and also in this case, right, the weight vector points toward the side with the positive examples on it. Right? Because those are the ones that have high dot product with the weight vector, and the negative examples are on the side away from the weight vector. So that's still going to be true here. The direction you shift it is going to depend on, right? So we'll have a weight vector W1, W2, W3, right? And we know, just like before, that we can scale the weight vector and it doesn't change the decision boundary. Right? So I'm going to scale it so that it looks like, excuse me, W1 over W3, W2 over W3, actually over absolute value of W3. And then here it'll be either a +1 or a -1, depending on whether W3 was positive or negative. Right? So I can scale it by any positive amount without changing the decision boundary. If I scale it by a negative amount, it'll flip which side is positive and which side is negative, right? So I'm going to just assume, I'm going to pretend that my weight vectors are of the form W, W1, W2, and either a +1 or a -1, right? And then I can plot W1 and W2, right? And the +1 and -1 will determine, it'll actually determine something that's maybe a little bit subtle. The first time I saw this, I was like, why does it determine that? But here we can tell that it's a +1 because the decision boundary, the direction from the origin is opposite to the direction W is pointing, right? So this would be a +1. If we had the same weight vector with a -1 as the last coordinate, man, that's a bad drawing. Let's try that again. There. We would put it here. It would be parallel and shifted the same amount in the opposite direction, right? So the weight vector, basically this plus or minus 1 determines which way the weight vector is shifted from the origin. And the length of the weight vector, right? So I can get, right, the norm of the vector W1 and W2, right? And that's going to determine how much it's shifted. It turns out that larger norms mean smaller shifts, and smaller norms mean larger shifts, right? So if I had this weight vector here, right, in the same direction, it would turn into something here, right? It would shift it more in the same direction. Okay? So you don't have to necessarily remember this. It turns out you can work this out with just a little bit of algebra that I'm not going to go through here. But the thing to remember, right, is that if you have a 1 on the end of your examples, you can still visualize them in one fewer dimension, the dimension that they were before you added the 1. And what it means is that you'll have a decision surface that doesn't go through the origin. And from the coordinates of the weight vector, you'll be able to determine what's the normal to that decision surface and how much is it shifted away from the origin. Yes?
So in 3D space, it does go through the origin of that. And
right.
1 or -1 would just be reflecting the plane or something?
Right, right. So if this projector projected 3D images, you would see that there's a half space in 3 dimensions that's going through the 3-dimensional origin. And then we're taking a slice through the plane where the last coordinate is 1, right? And then in that slice, it doesn't go through the origin of that slice anymore. All right? All right, so my advice is think about the case where you don't have the last coordinate equal to 1 because this picture is simpler than this one. But it's nice to know that this picture exists if you ever happen to need it. Okay? All right, so now we'll try, assuming everything goes well, to do a demonstration of the perceptron. So let's see if we can. There we go. All right. So what do I have here? I randomly spread a whole bunch of points around the unit circle. I picked a random decision boundary. I got really lucky because it looks like this decision boundary correctly classifies almost every example. That doesn't happen in general, but of course weird things happen whenever you do a live demo. So let's run the perceptron algorithm, right? So you'll see there's a little square around one of the training points. That's the training point that I'm randomly selecting, right? And so I've selected that point. That point's correctly classified, and so I'm not going to change the decision surface. So I'll keep going, selecting more. It's going to take a while until we happen to randomly pick that point. Yeah, maybe I should start it again, get less lucky. There we go, right? So it moved the decision surface, you can see, when I finally selected this point right here, right? And so now this one is incorrectly classified, and these guys are all incorrectly classified. So hopefully it'll take less time till I select one of those, right? So here I've selected this one. I've updated the weight vector, right? It was here. I've added this thing times its sign, which is -1, right? So I moved in the opposite direction from that from that example. The weight vector updates from here to here, right? The decision surface was this one with the normal that's this weight vector. The new decision surface is light, the light line, right? And its normal is the new weight vector, right? And so I can keep on cycling, And now, actually, after only a few examples, I have perfect classification because I got a lucky initialization. And no matter how many more of these I do, it should never update the weight vector, right? So, all right, let's do maybe another example, which is hopefully a little bit less lucky.
What is that circle on the right side?
Right, so this circle over here, this is the unit norm weight vectors, right? And so I've started with a weight vector of unit norm in a, basically what I did was I picked a random example and had it be in the direction of that example. And again, we got pretty lucky. There's only 2 misclassified examples. I never get this lucky when I'm actually trying to run machine learning software. But of course, because I'm trying to show something interesting happening, it works. Yeah, go ahead.
So again, like the higher the variance in the points, the more specifications you get?
Right, so because the points are spread all around the unit circle, I would expect to get a fair number of misclassifications. Expect to and actually do are apparently 2 different things. But yeah, the weight vector should be approximately uniformly selected. Basically, the way I picked a weight vector was I picked a random example and picked a weight vector that classified it right. Right? And so on average, right, like I should be misclassifying most of the other examples of that same class. All right, but if we run it for a while, right, it'll eventually, there we go. And one update and it gets the right thing. So you guys should all be apparently convinced that the perceptron algorithm is the greatest thing since sliced bread at this point. But I swear it doesn't work that well usually. Another question? No. OK. So what happens if you have noise, right? It ought to not work quite so well with noise. So I'm going to put I'm going to randomly flip the labels of 10% of the points. I'll actually put in a lot more points. All right. So this is 100 points. OK, good. Finally, I have a lot of errors. So I've randomly flipped the labels of 10% of the points. And now what I'm going to do is, right, so the very first time I misclassified one, I updated the weight vector. And now you see there's a black dot on the right-hand plot, right? Right here, this black dot wasn't there before. This black dot is going to show the average of all of the weight vectors. You remember I said in the case where there's noise, you shouldn't pay attention to the most recent weight vector, but the average of all of the ones you've seen so far. And so that one's going to be the black dashed decision boundary. All right? So let's run this for a little while, right? I make another mistake, right? And you can see, right, that the average, because the weight vector is staying in the same place, the average is getting closer to it. Eventually, I'll misclassify something. There we go. And it changes again, right? And so if I go for a long time, you can see that it's moving around. But after a while, it converges so that the average, right, the blue line is jumping all over the place. And it will keep jumping all over the place forever. On the right-hand plot, the blue dot is jumping all over the place. But the black dot is starting to settle down. And the same thing with the black dash decision boundary. And so if I stop it here, right, you can see that so the blue decision boundary is doing something crazy, but the black dash decision boundary is doing something quite reasonable the whole time, right? So that's the perceptron algorithm with and without noise, right? And the main difference is that with noise, which is the situation you're actually in most of the time, you want to keep track of the average of the weight vector. All right? And just for completeness, I can show you what happens when you have an intercept, right? So here now I have something with an intercept. And the difference now is that the line doesn't go through 0, but it does pretty much the same behavior, right? It's sliding around, doing basically reasonable things. And while the blue line is going all over the place, the average is starting to settle down to a very reasonable classifier, right? And so basically the only difference from a qualitative sense here is that the classifier doesn't go through the origin. But if you want to back out what the weight vector is from the visualization, you should study the slide that I had on homogeneous coordinates. All right. So are there questions? Yeah.
So we choose the black line and as the boundary line?
That's right. So you would use the black line. You would use the average of all of your weight vectors instead of using the most recent one. You can actually prove some results if you choose a random weight vector out of your past, but the average is going to have lower variance than a random one. Yeah?
By the average weight vector, you mean the average of the weight vector at each stage in the algorithm?
That's right.
Or it's not running the algorithm multiple times in the same data sets and then averaging the weight vectors?
You could do that too. So the choices were run the algorithm once and average all the weight vectors that you see in that one run of the algorithm, and that's what I'm suggesting. The alternate was run the algorithm multiple times and average the weight vectors at the end of all of those runs. And that also will produce reasonable results, but it's more expensive. Yeah?
It looked like, just from that example, it was, for cases where it's classifying correctly, it was using the unchained version again.
Mm-hmm.
So you're using each
That's right.
time it's another way to vote for like, yes, it's the
That's right. If you have a like those reality shows where if you win, right, you're the champion and you stay there, defeating challengers until you finally get knocked off of the hill, right? So your weight vector stays, it keeps getting a vote every time until it's wrong. And then it gets knocked off the hill and the new challenger replaces it and becomes the champion. Yeah?
So since you're taking an average, if you have a lot of points in one side of the decision boundary, I mean, if a lot of yi's are actually 1 and very few are -1, do you think this could push the wi's into one direction?
Right, so you're not taking an example of, you're not taking an average of your examples, right? You're taking an average only of your weight vectors. But you're right in the sense that if the class, so what you described, if you have a lot of examples of one class and very few examples of the other class, that's called class imbalance. And it does make life more difficult for learning algorithms. The perceptron will still work, but you will update more often on one class than the other. And you can get to the situation, like if you have a very large number of examples and they're fairly low dimensional, you can get to the situation where all of the capacity of the linear decision rule is used for the majority class, right? And you're essentially ignoring the minority ones because they just don't happen very often. And there are tricks you can do, like, for example, if positive examples are only 5% of your data set, you can just update 20 times as much. I guess 10 times as much because you expect them to be 50%. Whenever you make a mistake on a negative, on the positive example, on the minority class, right? But yeah, this is an area of active research, is how to deal with extreme class imbalance in machine learning problems. More questions? All right, so cool. Let us get rid of the demo then. And come back to our slides. All right, so now we're going to start looking at the theoretical analysis of the perceptron. And we're not going to get through it. We have 10 minutes before the end of class. We're not going to get through the whole theoretical analysis, but we'll get a start on the major concepts that you're going to need to know, and we'll continue the analysis later. All right, so to the concept that's going to be most important for the theoretical analysis of the linearly separable perceptron is something called margin. So I'm going to draw a picture of it, and then I'm going to go through the definition, right? So let's look at the optimal classifier, which is probably something like that, right? I guess that's not perfect. It's probably something closer to that. Right, like this, right? And so let's look at the distance from, or actually the angle between, right, the optimal classifier and the nearest example to that, right? So basically we make a mistake. If one of these points crosses over the line, I'm going to take a look at the point that gets closest to crossing over, right? And I'm going to call the margin some function of that angle. Okay? So what we're actually going to do, the mathematical definition, is we're going to take our weight vector. We maximize over all weight vectors of unit norm, right? So here's the unit norm weight vector for this classifier. We also maximize over the ones that are less than unit norm, but in fact the maximum will occur on the unit norm ones. Then we minimize over training examples, so we take the training example closest to the boundary, the dot product between W and UI, right? So if we look here, right, this will be the minimizing UI. Right, and so this will be here the maximizing W, right? And the margin is then going to be UI dot W for that I and that W, right? So we'll take the classifier that has the best possible separation and then take the example that has the least separation, and that's going to be our margin, right? The dot product between the two of those. And because they're both unit norm, what this dot product is, that's going to be the cosine of theta, where theta is, well, I'll draw it on the figure, right? So here, right, theta is that angle. Right, UI is unit norm because I did it that way in this example. In general, all you have to do is have your examples be normalized so that they have some maximum norm. And then the theta, it's a little bit less easy to interpret what the margin means in that case. But this definition holds in that case as well, right? So I here drew them so that every example has unit norm. But the definition works as long as they have bounded norm. If they didn't have bounded norm, well, there would be infinitely many of them. But if they didn't have bounded norm, then this angle could be made arbitrarily small as you went to bigger and bigger examples, right? So you assume your examples have bounded norm, and you look for this max over weight vectors, min over examples of this dot product. Okay. All right, so that's margin. What we're going to be able to prove is that if there's a large margin, right, in other words, if the examples are not just linearly separable, but they're linearly separable and you can stay far away from them, then the perceptron's going to converge quicker. And if there's a small margin, it's going to converge slower. And if the margin is negative, we're going to have to prove a different theorem, right? Or zero. If it's zero or negative, we're going to have to prove a different theorem. Right? And so how large is the margin going to be? You know, depends on your data set, right? But the nice thing to note is that nowhere in this formula is the dimension of the examples mentioned at all, right? So what that means is that we're basing our analysis on a quantity that doesn't have to depend on the dimension. So the perceptron could work potentially very well in 1 billion dimensions with only 10,000 training examples, which is kind of a cool thought, as long as in those billion dimensions there's a good margin, right? So that's kind of cool. And in the worst case, not going to derive this, but in the worst case, even for linearly separable data sets, the margin gamma can be exponentially small in the, let's say, the bit length of your examples, right? So in the worst case, the margin is horrible, right? Exponentially small means that perceptron essentially doesn't converge. It will converge, but not in poly time, right? But we don't design for the worst case data set, right? We design for data sets that we're likely to see in practice. And in practice, especially once we get to the noisy perceptron analysis later, we're going to be able to say that a large margin is a pretty decent assumption. Okay, makes sense? All right. So the next thing in my slides is the perceptron proof. I am 100% sure that I can't go through that proof in 3 minutes. So I think I'm not even going to start it. I'll start it next time that we talk about perceptrons. Yeah, so I think we'll just end there, and if anybody has any more questions, come on down and ask me.